In this video, I'm going to go over this worksheet, show you how you get to the solutions, and give you a basic idea of how you do everything. So let's just start at the first problem, where you have this wave, and you're trying to figure out some of the values, like the amplitude or the wavelength, and we'll get to the other parts in a second. So the first thing you should do when you see a wave equation like this, is you should compare it to the general wave equation that you have on your formula sheet. And by looking at these two, if you know what the symbols mean, you can pretty much figure out any of the values. Amplitude is just the value A. So if you compare this equation here to the equation from the formula sheet, A is obviously just going to be 50. So we can write that down. That's fairly easy. Now when we're looking at the wavelength, we have to look at the components of both equations that deal with wavelength. Wavelength is this little lambda symbol you see right here in the denominator. So what you're doing is comparing 2 pi over lambda to what we have up here, 2 pi over 4. If you do that and you set them equal to each other, you can tell that lambda automatically is just going to be 4. Now let's look at period and how we find the speed. Once again, you're just comparing it to the same equation, but now if we're looking at period, period is the capital T that we see right here. So if you compare this term with the term we have over here, and just like before you set them equal to each other, we'll have 8 pi is equal to 2 pi divided by t, again where t is the period. If you solve for t by multiplying it to the other side, and then you divide by 8 pi, you end up with t is equal to 1/4, or 0.25 seconds. So that's how you get the period. Now we need to look at the speed of this wave. Now, there's no one term in here that gives us the velocity, so we have to find out in some other way. When you're looking at velocity of a wave, two equations should come to mind. The first one, as we'll see right here, is v equals lambda times f. And that's velocity is the wavelength times the frequency. We already have the wavelength because we did that in part B. We don't yet have the frequency, but it's not that much of a jump. Because if you remember, your frequency is just equal to 1 over your period. So since we have the period as 1/4, the frequency is going to just be 4. So if you put that in, we have 4, which is the wavelength, times 1 over 0.25, and this right here is just 1 over the period, which is frequency. That gives us the answer of 16, like we're looking for. So now we have a wave. It gives us the length of the wave, how much tension it's under, and it gives us the mass per unit length. The first thing it's asking for is what is the speed of the wave. And this is the second equation that should come to mind when you think about speed of a wave. The first one we had was v equals lambda f. That doesn't really apply here because we don't have the wavelength and we don't have the frequency, so that equation kind of doesn't do anything. Instead, we have this equation, which says velocity is the square root of the force divided by the mass linear density. And that mass linear density is just mu. So if we look at this, the force is just the tension, which is 5 newtons, so that's not that difficult. The mu, however, is a little bit confusing. Like I said, it's the mass linear density, which means it's the mass per unit length. And if you read through the problem carefully, you'll notice that is right here, 2 grams per meter. If that had given you just the mass, you would have to then divide by the length it gives you up here. But since that is already the linear mass density, that right there is mu, and you don't have to divide by length because its units are already grams per meter. So it's the right idea. We do need to convert from grams, though, to kilograms. So if we just do that by dividing by 1,000, we get that mu is 2 times 10 to the minus 3 kilograms per meter. So we plug that in with the force, and we get 50 meters per second for the velocity. Just to reiterate, when you're looking for velocity of a wave, you should either use this equation, v is square root of f over mu, or you should use v is lambda times f. If you have wavelength and you have frequency, use the second one. If you have any sort of force, you're generally going to use the first one. Now this problem is a continuation on the one we just saw. We're now looking at how the wave looks so we can find the wavelength and the frequency and all of those things. When you're dealing with this, it's important to have an idea of how the first wave will look, the lowest frequency or the fundamental frequency, and then go from there. So if it's fixed at both ends, that means it has to end and start at the same place, and the wave can only look like this. This is how a first harmonic is going to look. If you look at your formula sheet, there's an equation that gives you the wavelength from this. Now here, you notice it has an n right there. That n is the number of antinodes in your wave. The antinode is the maximum value of the wave. It's like the crest. So in this case, since we only have one antinode, the value of n is 1. And that's because it's the first harmonic. Plugging that in, using the length that we had in the previous part, which was 3, we end up with 2 times 3, which is 6. And the length, again, is 3 meters long. So what this is saying is that the wavelength is 2 times the length. And that just makes sense here. If you try and follow this wavelength, you go up, but then the wavelength has to go back up like that after it goes down. The entire wavelength is twice the length of the string. And so we see that the wavelength does make sense that it would be 6. Now with that in mind, we have to now find what the frequency actually is. This is where we use the velocity that we had in the previous part. Because we now have the wavelength right here, we have the velocity from previously, so since wavelength times frequency is the velocity, you can solve that for frequency to get that it's velocity divided by wavelength, and that's going to give us 8.33 hertz. Now, part C, we do basically the same thing. The difference here is it's now the second harmonic. So what do you think the second harmonic would look like? If you guess that it has 2 antinodes, you are correct. Once again, the antinodes are the maximum points right here. So since it has 2 antinodes, you put in the same equation, but now n is going to be 2. Again, because it's the second harmonic. With n being 2, that means the wavelength is just 3. Which makes sense because if you draw out the wavelength, it's going to look just like that. Do the same thing we did previously. Now the wavelength is 3. If we then use velocity equals lambda times frequency, we find that the frequency ends up being 16.7, which is twice the frequency of the previous part. And that's where the harmonics come in. The second harmonic has twice the frequency as the first harmonic. And the third harmonic would have 3 times the frequency, and so on. So if you know the frequency of the first harmonic, you can find the frequency of any other harmonic without really going through this math. Lastly, let's look at this intensity. This one is actually fairly easy to understand how to do it, but then there are some issues with the calculator. So all you really need to do when you're dealing with intensity and you want decibels is you have this equation here, where the beta, that fancy B right here, that is the decibel. So beta is equal to 10 times the log of I divided by I naught. I naught is just a constant. It's something you're given, it's on your formula sheet, and so you don't have to really worry about it too much. I is the value of the intensity you're looking at. So here we have this intensity of 10 to the minus 9. What this equation does is it takes that value of intensity and it transfers it from watts per meter squared into decibels. So if you just plug in these values, you'll end up getting 30 decibels as your answer. Now, the main issue I saw here when students were working on this is how they put it into the calculator. So you hit the log button. You don't have to hit log 10 because your computer generally has log as log base 10. And you need to make sure you have plenty of parentheses. What a lot of people did is they had log 1 times 10 to the minus 9 and then divided by 1 times 10 to the minus 12. And they put this in their calculator just like that. The problem here is that your calculator will then look at this term. It'll divide by the 1, but then multiply by the 10 to the minus 12. And that's not what you want. In order to solve this, just make sure you have one extra set of parentheses right around here. Doing that will ensure that you're dividing by not just the 1, but the 1 times 10 to the minus 12. So make sure you have plenty of parentheses in this equation. Now it's changing the intensity for part B, and we're trying to find out what happens to it. If you decrease the intensity, notice we're going from 10 to the minus 9 to 10 to the minus 6. So we're decreasing it 3 factors of 10. What that ends up doing is if we use the exact same equation, we now end up with 60 decibels. So what happens here is that any factor of 10 that we change from the intensity changes the decibels by a value of 10. Right? So the decibels increased by 30 at the same time that the intensity decreased by 1,000. So any factor of 10 in the intensity leads to a change of 10 in the decibel. So if we were, for example, to increase it once more, one more factor of 10 to 10 to the minus 5, you would expect the decibels to go up by 10 once again, so it would be 10 decibels. And that is basically the takeaway here.